Yeah, apologies again. Still learning the ropes on this high definition. There are differences from the previous standard method, but I'm learning. I think I understand what's going on now. All right, trying to get my brain back into what we were talking about. Okay, so the intersection points here, or the two sets of graphs, the square root thing, they're these curves. For a given value of gamma, you'll get a different curve, right? So here's this curve as a function of x, square root of gamma over x all squared minus 1. So for gamma is 1, you get this curve for different values of x. For gamma is 2, you get this curve, and so on. For gamma is 5, and so on. And so you can have an infinite number of curves. And as gamma increases, these curves move out more and more to the right. Okay. And so they're the square root type curves. And then you've got the cotangent, well, minus cotangent of x, those curves. And they'll scream up every pi, 2 pi, 3 pi, 4 pi, and so on. Right? So as your gamma gets larger and larger, and this square root thing, curve, will move more and more to the right, and therefore it will intersect with more and more of these cotangent curves. Okay, so effectively, you could have an infinite number of intersections, so long as your gamma is large enough, right? Okay, now let's look at the graph a little bit. So I was just saying a little bit before. Now x is positive because we're just taking the right hand part of the parity situation, and then once we know what's going on in the right hand, we can deduce what's going on in the left hand for the even and odd parity cases. Alright, so x is positive or 0. Just saying before that gamma over x is equal to this, which is greater than 1. Alright, and therefore the square root thing is positive, so we're only talking about the positive quadrant, the upper right hand part of the x square root graph, if you like. Okay, now what values of when does this become 0? In other words, where do these curves intersect on the x-axis? Well, can you see it'll just be when x equals gamma. So if x equals gamma here, then well, that's just 1. Minus 1 is nothing. Okay. So now the first cotangent curve, this one, the first one, it starts at pi over 2. That makes sense to you? Remember, now it's cotangent, right? It's 1 over the tangent. Now the tangent of pi over 2, tangent of 90 degrees, is infinite, right? So 1 over, that's 0. So your cotangent will start at pi over 2. Okay. So if and your gamma cuts this axis at your square root curve, this one cuts the x-axis at gamma. When x equals gamma, this becomes 0. All right. So if our cotangent starts at pi over 2, then since this curve cuts the x-axis at gamma, right? So that means if gamma is less than pi over 2, there won't be any intersections. Like you see here, gamma's 1. That's less than pi over 2, and there's just no intersection of this curve with the first cotangent curve. There's just no intersection. And if there's no intersection, there's no energy, what's the word? Allowable. There's no allowable energy because there's no intersection. It's only at these intersection points that these two sets of curves agree, they cross, they meet, and therefore the value of x for this curve is the same as the value of x for that curve, kind of thing. They meet, and that means the two conditions are met. And we derive these conditions from the conditions on the waveform, the wave function, single valued, normalizable, continuous, those sorts of things. Okay. So there's just no solution for x less than pi over 2, and you'll get your very first one when this when gamma actually equals pi over 2. Well, yeah, here that'll be your very first one. Okay. So for when your gamma is less than pi over 2, just no intersections, therefore no energy levels. There are no allowed energy levels. There just aren't any. Right? Now, how about in the region, say, between pi over 2 and 3 pi? In this region, well, there'll just be one intersection. Okay? So there should be one allowed energy for that range of x. Okay? So, and all right. Well, how about between 3 pi over 2 and 5 pi over 2? Well, then you get two intersections. Okay. So you have two allowed energies. Now, I was saying this a little bit before, but as your gamma keeps increasing, you'll get more intersections, because this curve just moves out to the right with larger gamma, and it'll be cutting more and more of these cotangent curves. Every pi. Every pi there's another one. Okay. So effectively, you can have, as gamma just keeps getting very large, you can have infinitely many cuts, and therefore infinitely many energy levels. Okay. Now, we were doing this for the odd parity case. Now, for the even parity case, here, the appropriate condition was that not the cotan, but the tangent alpha A is beta over alpha. So I'm asking you as homework, do the same analysis, all this kind of analysis on this left-hand side of this session and the right-hand side of the previous session. Do the correspondingly similar analysis for the even parity case using this, and you'll get something similar. All right. All right. Now let's have a little bit of discussion about these results. So the number of cuts, like here, there's 2, there's 1. The number of cuts will depend on the value of your gamma. Makes sense? The higher gamma is, the bigger gamma is. This curve moves out to the right, cuts more and more of these cotangent lines, giving you more and more intersection points, and those intersection points correspond to allowed energy levels, right? Quantized energy levels. Okay, so so number of cuts, number of energy levels depends on your gamma. Now, go back previous session to the definition of gamma, and you'll see that it's proportional to the square root of your V naught, your potential value, finite potential value, times a squared. Okay, so gamma is proportional square root of VA squared. So this term here, you can look on it as a kind of strength, because as your V deepens and as your A widens, right, then your gamma goes up. So this product, or square root of the product of V and A squared, is a measure of in a manner of speaking, the strength of the well, the potential well would look like this. Right? So as your V gets larger, the potential well gets deeper, and as A increases, your well, this well, gets wider. Right? And that translates into a larger gamma. Okay? And the bigger your gamma, the more intersection points, therefore the more allowed energies. Okay? So by increasing the depth of your well and the width of your well, you can increase your gamma and hence increase the number of allowed energies. Okay, I hope you follow that logic. All right. Okay, so both these factors, the depth of your well and the width of your well, A, they both push up, so both increase, they push up your gamma, and hence the number of energies. Now in the limit, you can have infinitely many energies, right? Until, and then here's where the correspondence principle comes in. We'll be talking about that more and more. as this course goes on. In the limit, you get infinite number of energies, and then the difference between those energy values effectively washes out to zero, and then you get the classical mechanics conditions. In a sense, you're saying that your quantum mechanics merges almost merges into smooth, continuous, classical mechanical type behavior predictions. Right? Okay, so a bit more discussion now. Why are there no allowed energy levels in this range when x is between 0 and pi over 2? Why no energies? So why no energy levels for when gamma is less than pi over 2? Now, look at the definition of gamma. So if gamma is less than pi over 2, then gamma squared is less than pi squared over 4. And then from the definition of gamma, you can rewrite this condition as this, right? So you get v naught a squared is less than pi squared h bar squared over 8m. Right? That just comes out of the definition of gamma, so look it up. Well, if you have this kind of condition satisfied, that goes against, like if you're, if this is less than this, then you get a violation of the Heisenberg uncertainty principle, right? Which we'll show now. So you can't have this less than this, because if you did, you get a violation of the Heisenberg uncertainty principle, the HUP, right? Well, let's show that's true. Now, the uncertainty in the position, we've done this sort of thing before a little. The uncertainty in the position is about A, right? That's the width of your well. Particles in there somewhere, but you're not sure where. So there's an uncertainty in the position that's more or less of magnitude A. Okay. Now, from the Heisenberg uncertainty principle, that means that the uncertainty in momentum, so delta P, will be of the order h bar, well, h over A, right? This A here now is your delta x. So I've taken delta x, delta P is about h, and I've taken the delta x underneath here. Okay. So now we have an expression for the uncertainty in the momentum, which is sort of h bar over A. So the uncertainty in the energy, kinetic energy, will be delta P squared over 2m, right? But delta P is h bar over A. So here you get h bar squared over A squared times 2m, right? Okay, now if this what is this now? This is the uncertainty of your energy. So if this energy uncertainty is larger than the depth of your potential well, so if this here is larger than your V naught, then there's so much energy it can get out from the well, right? It won't be stuck in the well. It'll just get out. So you won't have your eigenstate, your wave function, will not be bound. It won't be stuck, confined in that well. Right? It'll be strong enough, in a sense, to get out. So in other words, another way of speaking is the well then, and I'm quoting here from the text from Davies' text, because it brings in a little bit of philosophy as well, which I'll mention in a minute. Okay, so if this uncertainty in the energy is larger than the depth of the well, the potential well, V naught, then to quote Davies, then that well is not strong enough to overcome the irreducible quantum agitation of the wavicle. Now that will happen when V and this are more or less the same size. Okay, so in other words, V naught is about this. Here it is here, and so bring the A squared over this side. So then you've got V naught A squared is roughly h bar squared over 2m, and that is of the same order of size as roughly pi squared h squared over 8m, which is here. Okay. Right? So if you had